free lunch. Practices. Practices and principles used in regenerative farming include alternative food networks, AFNs, commonly defined by attributes such as the spatial proximity between farmers and consumers. Aquaculture, ecological aquaculture, regenerative ocean farming, agroecology, agroforestry, biochar, terra preta, borders planted for pollinator habitat and other beneficial insects, compost, compost tea, animal manures and thermal compost, conservation farming, no-till farming, minimum tillage and pasture cropping, cover crops and multi-species cover crops, home gardens to mitigate the adverse effect of global food shocks and food price volatilities, also as a strategy to enhance household food security and nutrition, regrowing vegetables for recycling and sustainable living, keyline subsoiling, livestock, well-managed grazing, animal integration and holistically managed grazing, grass-fed cattle, natural farming, natural sequence farming, organic annual cropping and crop rotations. Perennial cranks to prevent soil erosion, also known as grading banks and, in parts of Australia, commonly known as Purvis banks, after Ron Purvis Jr. of Woodgreen Station in the Northern Territory. Permaculture design, polyculture, and full-time succession planting of multiple and intercrop plantings. Silvopasture, soil food web, environmental impacts, carbon sequestration. Conventional agricultural practices such as plowing and tilling release carbon dioxide (CO2) from the soil by exposing organic matter to the surface and thus promoting oxidation. It is estimated that roughly a third of the total anthropogenic inputs of CO2 to the atmosphere since the Industrial Revolution have come from the degradation of soil organic matter, and that 30 to 75% of global soil organic matter has been lost since the advent of tillage-based farming. Greenhouse gas (GHG) emissions associated with conventional soil and cropping activities represent 13.7% of anthropogenic emissions, or 1.86 pgCy-1. The raising of ruminant livestock also contributes GHGs, representing 11.6% of anthropogenic emissions, or 1.58 pgCy-1. Furthermore, runoff and siltation of water bodies associated with conventional farming practices promote eutrophication and emissions of methane. Regenerative agriculture practices such as no-till farming, rotational grazing, mixed crop rotation, cover cropping, and the application of compost and manure have the potential to reverse this trend. No-till farming reintroduces carbon back into the soil as crop residues are pressed down when seeding. Some studies suggest that adoption of no-till practices could triple soil carbon content in less than 15 years. Additionally, 1 pgCy-1, representing roughly a fourth to a third of anthropogenic CO2 emissions, may be sequestered by converting croplands to no-till systems on a global scale. There is mixed evidence on the carbon sequestration potential of regenerative grazing. A meta-analysis of relevant studies between 1972 and 2016 found that holistic planned grazing had no better effect than continuous grazing on plant cover and biomass, although it may have benefited some areas with higher precipitation. However, some studies have found positive impacts compared to conventional grazing. One study found that regenerative grazing management, particularly adaptive multi-paddock (AMP) grazing, has been shown to reduce soil degradation compared to continuous grazing, and thus has the potential to mitigate carbon emissions from soil. Another study found that crop rotation and maintenance of permanent cover crops help to reduce soil erosion as well, and in conjunction with AMP grazing, may result in net carbon sequestration. There is a less developed evidence base comparing regenerative grazing with the absence of livestock on grasslands. Several peer-reviewed studies have found that excluding livestock completely from semi-arid grasslands can lead to significant recovery of vegetation and soil carbon sequestration. A 2021 peer-reviewed paper found that sparsely grazed and natural grasslands account for 80% of the total cumulative carbon sink of the world's grasslands, whereas managed grasslands, i.e. with greater livestock density, have been a net greenhouse gas source over the past decade. A 2011 study found that multi-paddock grazing of the type endorsed by Savory resulted in more soil carbon sequestration than heavy continuous grazing, but very slightly less soil carbon sequestration than graze exclosure, excluding grazing livestock from land. Another peer-reviewed paper found that if current pasture land was restored to its former state as wild grasslands, shrublands, and sparse savannas without livestock, this could store an estimated 15.2 to 59.9 gigaton additional carbon. The total carbon sequestration potential of regenerative grazing has been debated between advocates and critics. One study suggests that total conversion of livestock raising to AMP grazing practices, coupled with conservation cropping, has the potential to convert North American farmlands to a carbon sink, sequestering approximately 1.2 pgcy-1. Over the next 25 to 50 years, the cumulative sequestration potential is 30 to 60 pgc. Additions of organic manures and compost further build soil organic carbon, thus contributing to carbon sequestration potential. However, a study by the Food and Climate Research Network in 2017 estimates that, on the basis of meta-study of the scientific literature, the total global soil carbon sequestration potential from grazing management ranges from 0.3 to 0.8 GeT CO2 eq per year, which is equivalent to offsetting a maximum of 4 to 11% of current total global livestock emissions, and that expansion or intensification in the grazing sector as an approach to sequestering more carbon would lead to substantial increases in methane, nitrous oxide, and land use change-induced CO2 emissions, leading to an overall increase